Okay, so we've talked about the derivatives of sums, the derivative of differences. We now can do a product and a quotient rule. Well, one thing we haven't talked about is how to handle composite functions. What happens when you have a function within a function? To do that, we're going to use something called the chain rule. So that's the gist of our discussion for today. But let's start with a little practice, shall we? Find the derivatives of each of those. I'll wait. I'm going to talk while you're working. Notice in the first problem I put a note on there. Are you going to multiply that out, then take a derivative, or are you going to use the product rule? Either option is viable. In the second problem, we have to use the quotient rule until we get done with the lesson today. After the lesson today, we will be able to change that quotient rule into a product rule. We can't do it yet, but after we talk about the chain rule, you'll be good to go. And what happens is people get very good at one and focus on using one of them instead of both. Oh boy. Don't bother simplifying either one of them. Just get your basic answer, and then we'll move on from there. We're a little crunched for time today. I want to try to get through the lesson in the 30 minutes we have left. All right, stop working for a second and give me an emoji. So if you multiplied it out, give me a thumbs up. If you use the product rule, give me a heart. Thumbs up if you multiplied, heart product rule. Interesting. About 50-50, not bad. Okay. And notice no judgment in my answer that you could use either method. They are viable. It's just a matter of which one works better for you. Some people just completely don't want to multiply that out. Do the product rule. Okay. It's entirely up to you. Okay. So I don't have answers for you. How far did you get, by the way, just for time frame? Did any of you get to the quotient rule problem? Okay, all right, good. So let me set these up. If you did it as product rule, we would get 3x squared minus 4x times 5x minus 4 plus x cubed minus 2x squared plus 7 times the quantity 5. And you're going to have to, if the problem required simplifying, you'd have to multiply it out anyways. Okay, good. Quotient rule setup. Changing colors here. We would get big honking gazenta bar, x squared plus 2, quantity squared on the bottom. Put the denominator on the bottom, square it. Bring the denominator up to the top. Times the derivative of the numerator. Minus big honking bracket, the numerator, times the derivative of the denominator. Okay? Distribution fun ensues. Make sure you're careful with parentheses. Let's suppose I don't have these parentheses here. It completely alters the value of the problem. You might not see that as a big deal, but it completely changes the answer to the problem. The same thing is true with the parentheses over here. If we get rid of these guys, okay, now all of a sudden you're in a world of hurt because the only thing that's being distributed is the -6. All right. So again, be careful with parentheses. Chain rule allows us to take the derivative of composite functions, which is what that says. This does present itself with some ugly simplifying problems, and we're going to have to talk a little bit about that. I mean, it's that thing that I just kind of been pushing to the side, but at some point today, or today's Tuesday, on Thursday, we're going to have to take a look at what it means to simplify these problems. Okay. And we got to do some trig stuff. Always do trig, and then you should be able to recite the state capitals. Anybody? Nobody?
You used to be able to.
Yeah,
But
used
I can't
to.
anymore.
Yeah. Animaniacs have a great song about. Do you guys know the Animaniacs, or are you too young? Yeah? We know the Animaniacs? Okay, good. They have the state capitals. They have one on the universe. They have one on countries of the world. It's just fantastic humor. Okay, so the chain rule. We're going to start with this derivative. Now, I could do that as a quotient rule. You know how to take the derivative of this. I don't think I'm going to go through the whole thing, but I can give you a basic rundown here. Denominator on the bottom, squared, bring the denominator up to the top. Don't forget parentheses times the derivative of the numerator, which is 0, minus parentheses. The numerator times the derivative of the denominator. So after all that business, we get -2 over 2x minus 7 quantities squared. Okay, good. That's nothing new. However, what the chain rule is going to allow us to do is rewrite this equation as 2x minus 7 raised to the -1st power. For those of you that don't like the quotient rule, and there's plenty of you out there, myself included, you can turn quotient rule problems into product rules, or this guy, which is a chain rule. Okay, now how to do it is going to take some discussion, but once we learn the chain rule, we'll be able to get that same answer of -2 over 2 minus x quantity squared for the derivative. And there's no right way to do it. If you like the quotient rule or you're good at the quotient rule, then stay with the quotient rule. If you want to use the chain rule, you're good to go. However, some problems will present itself where you're going to have to use the chain rule. Okay. Now, what's the chain rule say? Well, it's going to allow us to find the derivative of functions within functions. That's what a composite function is. This graphic shows you when you need the chain rule and when you don't need the chain rule. Okay? First of all, that is not a composite function. That's just two separate polynomials. None of these are composite functions. They're the sum or differences of terms that you can take the derivative of. Now all of a sudden, we start putting functions within functions, and we have to start using something called the chain rule. One of the other things that you need to be able to do is to recognize how many functions you're looking at. And we'll get to that a little bit later in the slideshow. Okay, so here's the chain rule. This, well, and this for that matter, probably don't make much sense. Okay, So I have an English version of it for you. There's an onion in that picture because we're going to talk about layers of the onion, like Shrek. Many layers. What you want to do is start from the outside of the onion and work your way inside, going through each of those layers. And each of those layers is a different function. This slide probably doesn't make much sense. It will start to make sense as you look at some examples that I have for you. Now, seeing the English version of this might make a little bit more sense. You have an outside function and you have an inside function. The outside function is f of x. The inside function is g of x. So take the derivative of the outside function times the derivative of the inside function. And again, confusing until you see it in action. So let's put it in action. Oh, that's kind of important. One of the things I mentioned is you want to figure out how many functions you're dealing with. We'll start with something easy. We'll start with 2 functions. You always chain 1 time less than the number of functions. If I have 3 functions, I'll chain twice. If I have 5 functions, I'll chain 4 times. The reason this is important is you will see problems where you can just keep chaining over and over and over again until eventually you get 0 and the whole thing's screwed up. So you got to rein yourself in a little bit and don't chain too many times. Okay, so here we go. 2x minus 3 raised to the negative 2 power. So question number 1, how many functions are there? Anybody? You're correct, Prasant. There is 1 function there, 2x minus 3. There's another function there. 2 functions, 1 chain. So we're laying the groundwork for attacking this puppy. Which function is on the outside? Raising to the negative 2 power or the 2x minus 3? It seems like a silly question, but it is relevant.
2x minus 3.
No, that's on the inside. We want the one on the outside. You had a 50-50 shot. It's okay. Thanks for the help.
Oh, you mean like literally? Okay, yeah.
Yeah, literally on the outside. Okay. Okay, so that means the derivative, I'm going to forget about this business for a second. And I'm just going to take the derivative of something raised to the negative 2 power. Well, how do I take the derivative of something raised to the negative 2 power? You bring the exponent down, you reduce it by 1. And then that stuff. Well, that stuff isn't important, but we do know it's that. Okay. Don't get obsessed with what's inside the parentheses. Just do the derivative of the outside function. Now a chain. We chain on the derivative of the inside function, which in this case would be a pesky little 2, because the derivative of 2x minus 3 is just 2. Clean it up. And we're good to go. If you're feeling all fancies in your pantsies, you could do this. Ooh. Okay, who's completely confused? Oh, I got a so-so. Okay, that's good. That's better than completely confused. Let's do some more examples because I think it will start to sink in eventually. Well, I hope it sinks in eventually because it's kind of important. Oh, look, there's all the work. Okay, great. Yeah. Oh, hey, I got all fancy here and I decided, whoops, in this second problem to multiply the whole thing out. Okay, change colors here to blue. 2 functions. Same as the first part. One inside the other. H prime of x. Forget about this stuff and just take the derivative of something raised to the fourth power. 4 times x to the fourth plus 3x squared plus 2x plus 1 raised to the third power. Chain the derivative of the stuff inside. Don't forget parentheses. 4x cubed plus 6x. Whoop, there should be an x there. Plus 2. No, you don't need to multiply out a cubic. This is the big thing about the chain rule, is that it allows us to not have to multiply these things out. Okay. Now, what do I mean by that? Well, notice in this problem, I could have written this as that and multiplied that beast out and done all this other garbage. You do not want to multiply out a quartic. So the chain rule allows you to not do just that. Okay? Okay, you do G. Christian, are you in a closet?
No, I'm in my basement.
Oh, it's really dark. It looks kind of Halloweenish the way you're lit up right now. Does it not, everybody? Aren't you a little afraid of Christian right now? Thanks for the help, everybody. Jerks. Christian, could you pick a number 1 through 5, please?
4.
And then 1 through 6.
5.
5. John, what do you got?
Yeah.
What do you got for an answer?
I don't have this one.
Say again, I'm sorry.
I don't have this one.
Oh. Okay. Does anybody?
I do, but I don't know if you, well.
Just give it to me, Allie. Just fire it off.
I got 4 times 4x to the third plus 3 to the third power, and then times 12x squared. But I wasn't sure, since you said to not multiply anything out, I wasn't sure if I was supposed to multiply the 4 times the 12x squared.
Well, let me ask the rest of the crew. Is that right? Yeah, good. Yeah, 2 functions. Function number 1, function number 2. The fourth power is on the outside, so we do that first, which is what this is. And then take the derivative of the thing inside. And no, you don't multiply that puppy out. Okay?
Okay.
Yeah, that's perfect. Well done.
Wait, so would that be the final answer for
Yeah.
the previous one?
Yeah, you leave it just like that.
Okay.
Okay? Okay, so this one gets a little nasty, so I want to work through this because we get into this realm of simplifying derivatives. Okay? So this is still 2 functions in one chain. The one function is a quotient rule. That's inside. And the outside function is a squared term. Now, could you, before you started, could I do this? Yes. But I'm still going to have to do a chain rule. So whether I do a chain rule in the beginning or in the end is irrelevant. So I'm not going to do that. I'm going to leave it like this. Okay. Two functions. The outside function is a squared term. So I'm going to do the squared term first. That's what this part of my answer is. Bring the exponent down, reduce it by 1. This mess is the chain. Okay? At this stage, I would be ecstatic if you could get to that. I should say when you get to that. I have the utmost confidence in your abilities. However, since the title of the slide is simplifying the derivatives of a power, at some point we're going to have to be able to simplify that. Now, how could you possibly simplify it? Well, if I look in the top here, I can do some work up there by simplifying. Distribute the 5, distribute the 3x squared combined terms before I start bringing this business into it. And so we get that. Distributed the 5 to the first two terms, distributed the 3x squared to those two terms. And then the fun started. Okay, so this came from those two. This just came down to here, and the 2 I just moved up to the top. And notice, x cubed minus 3 times x cubed minus 3 quantity squared is x cubed minus 3 quantity cubed. Do not multiply out denominators. Oops. And now this becomes, quite honestly, some very tedious Algebra 1 work. We could distribute out the trinomial with the binomial. I'm not going to do that. Now, the only reason I would do that is if I thought it would cancel with the denominator somewhere. It won't. It's going to give me a quartic up on top. Quartic's not going to cancel with a cubic. So I just leave it like that. The biggest problem you're going to run into with these issues is when do you stop? Okay. Could I do more with this? Yes. You could multiply that whole business out. And I don't have an answer for you. It's going to come through practice. When you recognize that you should stop and when you recognize you should go on looking for something to simplify. Okay? Trig, just like everything else, except I wanted to make sure that you understand the notation. You don't even need any of this stuff. Okay? I gave it to you just so I can say I showed it to you, but the derivative of sine is cosine. If it's the sine of u, where u is some other function, then you chain on the derivative of that, which is what this is saying. Let's suppose u was, come on, Reedy, you can do this. All right, one more time. Let's suppose u was x squared. Then you would take the derivative of the outside function, which is the sine, and you would chain on the derivative of x squared. And I got some examples to practice that. Okay. So notice this looks just like the one I gave you a couple days ago, except the u's became x's, and we've got those u primes on the end of them. It's just a chain rule. Okay, so this will be fun. How many functions?
Three.
What are they?
Sine squared, 4x in the 5th power. Might be wrong. I don't know.
There are 3.
Wouldn't it be sine and then like sine squared and then 4x to the 5th power?
Correct. Perfect. Okay. This is the same thing as, if this helps you visualize it, we just choose in trig to move that squared inside. So yes, Max, 3 functions. Yes, Prasant, those are my 3 functions. Now let's talk about the onion. Which one's on the outside? The squared, the sine, or the 4x to the 5th?
The squared.
Good. Which one's the next layer in?
Sine.
Good. And therefore 4x to the 5th. Okay. So 3 functions, 2 chains. Okay. Anybody? Fan? Anybody? Fan? No? Nobody?
Good one.
Thanks. Thanks. Waiting all year for that. Okay, let's take the derivative. Derivative of the outside. Forget about the stuff inside. Taking the derivative of anything to the 2nd power is this. Times that mess inside, which we'll come back to in a second. Reduce the power by 1. We get that. Times the derivative of the next layer of the onion, which the derivative of sine is cosine. And 2 chains is going to get in the way. That's my first chain. Second chain is the derivative of this, so I would have a 20x to the 4th. Okay, good, done. Now, cleaning that up a little bit, however, I would get, let's see, 40x to the 4th times the sine of 4x to the 5th times the cosine of 4x to the 5th.
Can you explain how you got the 20x to the 4th?
It's the derivative of that It's a derivative of that puppy. That's my last chain. So chain number 1 was the derivative of this. Chain number 2 is a derivative of that. Make sense? Okay.
Is that above the 4x to the 5th for a reason?
Just because, well, I could do it under here if you'd like. Put a box.
That's not like to the power though, right?
No.
Okay, good.
Oh, this? Oh, I see what you're saying. No, this is because 2 chains was in the way. All right, hold on. I'm having some technical difficulties here. Bloody hell. All right, never mind. Yes, that 20 is not an exponent. It should be down there. But again, when I had 2 chains on there, he was in the way. Just like when we introduced product rule and quotient rule, this is going to require some practice. The most you're going to get out of the practice, I phrased that incorrectly. The biggest thing you need from the practice is being able to recognize how many functions, how many chains. The derivatives are pretty straightforward. By now, none of these functions are difficult to take the derivative of. A squared function, a sine function, 4x to the 5th. No problem. It's getting them in the right order and knowing when to stop. Okay, so let's talk about this as far as, let me get 2 chains out of the way. One of the reasons why I said it's important to recognize how many chains you have is because if you look at this function, I could keep going with chains. Okay, I could then chain on 80x to the 3rd, the derivative of that. Then I could chain on 240x squared. Then I could chain on 480x, then 480, then 0. And you see that we go down that rabbit hole that causes all kinds of problems. Some functions allow you to keep going if you didn't know what you were doing. But we only want 2 chains. 2 chains? So therefore, this goes away. And you stop after the 2. Okay? We good? Hot diggity. This last slide, which is in your book, is a summary of all the derivative stuff we've done so far. It's just not written in very good, understandable methods. But this is the technical, I call this calculus speak, that explains everything that we've done. Okay? Constant multiple rule. By that you know that if you take the derivative of 2x squared, it's just the derivative of x squared multiplied by 2. Sum and differences, product rule, quotient rule, constant rule, power rule we've done ad nauseum, the 6 trig functions, and then the chain rule. All of that on one nice little page. Okay?